Hello, in this video we will discuss the languages that are not regular. So we will show how to prove that a language is not regular. Before that, let's discuss if these three languages are regular. Recall that for a language to be regular, we need to find a deterministic finite automaton or any equivalent model. We can find a regular expression or a non-deterministic finite automaton. We already have shown that we can convert from regular expression to NFA and also from NFA to DFA. So we showed that these three computational models are equivalent. So for now, we will say that a language is regular if there's a deterministic finite automaton or a finite state machine that recognizes it. For L1, it's the set of all strings composed of the symbol A. Okay, so we can here see that it's the same as saying A star. Okay, and we know this language is already regular since it's composed of the operator star applied on the simple symbol A. And as you might know, regular languages are closed under star. So without even drawing this finite state machine, we can say that this language is regular. For the second language, it's also composed of a concatenation of a list of A and a list of the symbol B. Since the number of A and the number of B are not related, we can say that this is equivalent to A star, B star. Okay, so it's the concatenation between two regular languages, and we know that this is a regular language. Okay, but now for L3, since we have a sequence of A followed by a sequence of B, for which the number of A is equal to the number of B, we cannot find a finite state machine for this. Even if we try to obtain a finite state machine for the first part and a finite state machine for the second part, we cannot concatenate here because finite state machine doesn't give us the possibility to count. Okay, if we will pass from this part to this part, the machine already forgot the number of A that are recognized to use it for the part of the letter B. Okay, so we cannot find a deterministic finite machine for this. So we can say that L3 is not regular. Okay, but if we don't find a deterministic finite automaton, does that mean that this DFA doesn't exist? No, we should find a way to prove it. We have to find a way, a concise approach to prove that a language is not regular. For this, we will use a property for regular languages, okay, that states that if a language is regular, for long strings, there should be a cycle. As you might know, a language is regular if there's a finite state machine that recognizes it. And a finite state machine uses a finite number of states. Okay? So for long strings, there should be a cycle. Look at this example here. This machine accepts strings with length 1 or length 2 or length 3. Strings that are longer than 3 are not accepted here. If we want longer strings, we need in general a cycle. For example, this finite state machine allows us to recognize strings of length 2 or more. With this self loop here at the end state, we will allow for infinite infinite number of strings with a length greater than 2. So in general, there should be a cycle if we want to accept long strings. Okay, take for example this cycle here. Okay, um, and this property for regular languages states that if there's a long string, as long as a special value p called pumping length, this string can be divided in three parts, x, y, and z, and this string can be pumped. Let's take, for example, this um, structure of a finite state machine. If we will have a cycle, let's say, for example, in the cycle, the string will be denoted as, or the substring will be denoted as y. Before that cycle, the substring will be x, and after the cycle, the substring will be z. Okay, so if we take the string that is longer than p, we can divide it into x, y, and z. Okay, and in this case, for each I that is greater than or equal to 0, this string xy to the iz should be in the language. Okay, because if you can go to the cycle once, so you can go twice, you can go third time, fourth time, and so on. Okay, y is greater than or equal to 0 because I may not enter to the cycle. Okay, I may pass directly to the part containing the substring z. And for this property, we'll choose y such that its length is strictly positive. Okay, there should be a cycle, so y shouldn't be equal to epsilon, and also xy should have a length that is less than or equal to the pumping length p. This property is known as the pumping lemma. This pumping lemma states that if a language is regular, then it has a pumping length p. There should exist some number p such that any string longer than p can be written as a concatenation of three parts x, y, z, satisfying that if we pump the part y, x, y to the I, z is also in the language for all I positive. And the second condition states that we have to choose y not empty. Also, the length of x concatenated to y should be less than or equal to p. Now we will show how to prove that a language is not regular using this pumping lemma. The idea is to make a proof by contradiction. We will assume that the language is regular and use the pumping lemma property, which says that there is a pumping length p. We will suppose that we have this length p, and we will find the string s that is longer than p, and we will show that it cannot be pumped. Okay, we will show that x, y to the I, z is not in the language. And we will examine all the pumping lemma conditions and show that these are not satisfied. And in this case, we will come up with a contradiction to what we already assumed, and we will prove that the language is not regular. Let's take an example here. The set of strings that are composed of a sequence of A followed by a sequence of B, such that the number of occurrences of A and B is the same. Okay, we will assume that this language is regular. So we'll say that there is a pumping length P, and we need to find a string and prove that it cannot be pumped. Okay, let's choose this string s equal a to the p, b to the p. Okay, we need a string that is longer than p, and this string is good enough. Its length is twice as p. Okay, so for example here, for sake of simplicity, let's take p equal 5. Okay, in this case the string will be 5a followed by 5b. Let's divide s into three parts, s equal x, y, and z, and choose the part that will be pumped. Okay, here we have three cases. The y contains only a's. The y is in the first part here. For example, a here will be y. This a before that will be x, and the 5b will be the string z. In this case, if, for example, I equals 2, so y squared will be 4a followed by 4a. And we'll report here the x, which is a, and the b's, which are 5b. In this case, you can see that this string is not in the language. The second case, y contains a's followed by b's. Okay, let's take, for example, this portion here, double a, b. Now xy squared z will have 5a followed by a b followed by double a followed by 5b, because we have to write AAB twice. Okay, AAB and then AAB and then the rest of B, which are already 4Bs. Okay, and as you may see here also, this is not in the form A to the N, B to the N. So it's not in the language. The third case says that we can choose the Y in the B part. Let's take these 3b as y. So xy squared z will be 5a followed by triple b 2 times because it's squared, and then the z, which is double b. Also, the number here is not the same for a and b, so this is not a string of the language. For a summary here, in the three cases, we find that when we pumped the string, the obtained string is not in the language. So we find a contradiction. The pumped string is not in the language. So we can say that L is not regular. Okay? And note that condition 3 of the lemma states that the length of xy together should be less or equal to p, and this can already eliminate cases 2 and 3. Okay, and work only on case 1, which states that the y should be chosen in the zeros part. That's the idea of the pumping lemma and how to use it to prove that a language is not regular. Thanks a lot, and tell me in the comments below if you need other examples for languages that are not regular and how to prove that with pumping lemma.